Hello, my name is Luis with TEC-EASE. Welcome to the GD&T Tip of the Month. This month we're going to be talking about form controls. This is the first of two episodes. We're going to begin with straightness and flatness. Well, let's begin, but before I do, we need to remember that Rule 1 actually addresses form with respect to features of size. What it states is that perfect form at maximum material condition is required. So if that's the case, think about this part, for example. If I set it up at the part and I understand the width and its max material tolerance, so say it was 5 plus or minus 0.2, MMC would be 5.2. I would set up my fixture so that would be spaced at exactly 5.2, and in order to pass inspection, the part should slide in and out of my fixture. Of course, let me stabilize that a little bit. And I'm improvising today to make my point, but you can see the part should slide in and out of the fixture in order to pass inspection. And so we also get parallelism for free there. Okay? So perfect form at MMC is required. One of the greatest errors that tends to occur is for folks that don't understand this rule. They end up over constraining their parts. Remember that Rule 1 states perfect form at MMC is required. Therefore, if you will, your plus or minus tolerance controls your form tolerance. I have this part here, and say the drawing indicates a flatness control on this surface. Well, in order to inspect that surface, I would have to set it up in such a way to actually account for flatness on a single surface. And the intention is that we're going to somehow set up and stabilize the surface, but this is a very unstable part. And so I'm going to apply some weight, improvise a little bit today with this V block here. And it's heavy enough to hold the part down. Of course, I could clamp it down, but parts are to be inspected in the free state condition. That's what the standard states. But let's just go along with this for now, and you can see that I can run the indicator along the surface, and this is a primary datum that I'm verifying. But as you can see, I've set it up on another surface. So what I'm really checking is parallelism. I'm checking the parallelism with respect to this surface that I've clamped down on. And so what I need to do is free up that surface. I do not need to apply force. What I need to do is stabilize the part. So let's just say that we can use other methods, but for today, I'm just going to set this part in the free state condition on that surface. And now I can set up the indicator and begin to lower it down. And of course, the indicator would be such that it would be touching the bottom of the surface, and I would tilt the indicator so that I could actually get underneath there and do that. So you can see I'm setting up the indicator. You want to make sure that the probe of the indicator does not make contact with the surface. You want to make sure that the spherical ball at the tip is actually making contact with the surface. So we have to be careful in the setup here. So I've tilted the indicator up so it's not going to make contact. And as I begin to run the indicator and make contact, again, we have to apply enough force to measure the variation. And now I've contacted, and now the indicator is moving. I know it's difficult for everybody out there to see what I may be doing on my end, but we have to be careful. But now, as you can see, I'm running the indicator. I'm going to slide it along the surface. It's in the free state condition, right? I'm not applying force. Now I'm checking the surface to itself. Once the surface has been accounted for, say I had a flatness of 0.1, the indicator should have not moved more than the total 0.1. Okay? Once I've done that, now I can place the part on the datum feature. I have a granite plate here, and the granite plate is very accurate. If you remember earlier, I talked about the 10% rule of thumb. And so say that I had a flatness tolerance of 0.1 here on the part. Therefore, the surface plate would at least have to be within 10% of that, which would be 0.01. We're much better than that in this case, of course. And so that would be your flatness. Now straightness, very similar to flatness. The only difference is now we're going to run the indicator along linear elements. And so I'm going to set up the indicator again, free state condition. And now instead of dragging the indicator all the way around, so in other words sliding it around, now I'm going to just run it along linear elements. Okay? So we need to understand that with straightness, we could get flatness for free depending on how I set up the part for inspection, how many linear elements I take along that surface. The common question is, well, how many linear elements do I inspect? Do I take 2 linear elements, 3? Well, that's definitely up to the inspector. It usually depends on the risk and the design intent. Design intent always determines the method of inspection. Well, I hope you enjoyed that, and we hope to see you next month. And remember, here at TEC-EASE, GD&T rules. Adios.